Hello students. So this lecture should come immediately after that first midterm. Although I suppose, well, second midterm? The first online midterm. We will have a goal in this lecture, which will be to begin to understand inverse functions to trig functions. And there's a reason to do that. If we're interested in doing things with trig functions, often we'll be interested in solving equations that involve trig functions. If I tell you that sine of x is 1/8, can you tell me exactly what x is? Well, in order to motivate how we'll do this, let's think about how we did this for exponential functions. When you have to solve an equation 3 to the x equal to 7, well, you can just write down a formula. You write down x is equal to the log base 3 of 7. In order to solve exponential equations, we introduced a new function called the log functions. And those solve as inverses to exponential function. If you want to solve 3 to the x equals 5, you know how to. It's x equal to the log base 3 of 5. And in some sense, all this is doing is giving a name to the solution of that equation. But once you give a name to something, you can start studying it. You can maybe teach a computer to do some computations and use that the computer can do those computations. If I want to solve something like sine of x equal to 1/8, I need to know how to invert sine. So the goal of today is to invert the trig functions. And let's start with this. Let's start by recognizing that that goal, as stated, is impossible. Trig functions do not have inverses. And, well, in order to see exactly why, well, let's just do a quick demo. Here's the graph of y equals sine of x. You can tell that it can't be cosine because it looks like it goes through 0, 0. So this is the graph of y equals cosine of x. And look at those two functions. Let's ask some questions. Are these functions one-to-one? So remember the horizontal line test. Draw a horizontal line. There is a perfect horizontal line. Didn't wiggle at all. How many times does that yellow line cross this graph? Well, I can visually see 4 of them. And you can imagine that if you continued the graph on forever in the x direction, you would see infinitely many points of crossing. But remember, what does it mean to be one-to-one graphically? It means that every horizontal line crosses the graph of the function at most once. Well, infinity is definitely more than 1, so sine of x is not one-to-one. Similarly, if I draw a horizontal line on the graph of cosine, I mean not every horizontal line, there is a horizontal line that crosses cosine 0 times, which is definitely less than 1. But here's a horizontal line that crosses the graph of cosine also infinitely many times. So cosine is also not one-to-one. Now remember, one-to-one functions are the functions that we can talk about inverses to. So do sine and cosine have inverse functions? Nope. And maybe seeing it graphically, more graphical stuff. So let's suppose I take the graph of y equals sine of x and I switch the job of x and y. So I guess that would be sketching the graph of x equals sine of y. I apologize, x equals sine of y. So because that's exactly what you do when you invert. So that will, so I'll take the graph of sine of x and I'll flip it over the line y equals x. I get something like this. But if you look at that, that fails the vertical line test. This is not a function. So, trig functions don't have inverses. If you try to invert them by just flipping over the line y equals x, you will get something that violates the vertical line test. But I still want to study inverses to trig functions, so I need to figure out how to get past that. And the truth is, we've already gotten past that in one case. So there's the function g of x. Is it one-to-one? Well, let's use the horizontal line test. Let's draw some horizontal lines. How many times does that line cross it? 0 times, so that's good. 0 is less than or equal to 1. How many times does that horizontal line cross the graph? Just once. 1 is okay. How many times does that line cross the graph? Twice. 2 is bigger than 1. So is this function 1 to 1? No. There exists at least one horizontal line which crosses the graph twice. So does g of x equal to x squared have an inverse function? No. But somehow, like if I asked you what's the inverse to x squared, you would have an answer, right? You would say the square root is the inverse to x squared, even though that's technically not quite true. Let's remember where the square root function comes from then. So here's the restriction of g of x to the domain 0 to infinity. So I'll only allow x values that are bigger than or equal to 0. There it is. Maybe for emphasis, one should put a solid dot there. Right? The point 0, 0 is included. Is that function 1 to 1? Well, let's draw some horizontal lines. 0 is less than 1. 0 is less than 1. 1 is okay. 1 equals 1. Yeah, all of those cross the graph of this function at most once. So is it 1 to 1? Yes. So does it have an inverse function? Yes. And let's go ahead and even sketch a picture of the inverse to that function. So I'll take this graph and flip it over the line y equals x, giving me something like this, which is, of course, the square root function. So the inverse to this function g is the square root of x. All right, so armed with that, let's go back to looking at sine and cosine. Let's use this idea of restricting the domain. We'll try to include x equals 0 in the domain, and we'll go as far to the right as we can without violating the horizontal line test. Then we'll go as far to the left as we can without violating the horizontal line test. That will tell us how to restrict the domain. And once we know how to restrict the domain to get a one-to-one function, we'll invert that one-to-one function. That will be what we will call the inverse to sine and inverse to cosine. So let's do that. So let's start at 0, 0. Start at x equals 0, which corresponds to y equals 0, on the graph of y equals sine of x. We'll go as far to the left as we can, while still having the function being 1 to 1. Looks like I can make it to that peak, because then it would turn around, start decreasing, and as soon as it starts decreasing, I would violate the horizontal line test. And then I'll do the same thing. I'll go back, I make it to there. And you'll notice that I'm filling in those endpoints with solid dots, because I can. I can fill in those solid dots without violating the horizontal line test. So, how far did that go? Well, remember this sine of x is equal to 1 at x equal to pi over 2. So I guess that's pi over 2 comma 1 at that point. And how far to the left can we go? Well, we get to negative pi over 2 comma negative 1. So I'll only use that blue bit of the graph of sine of x when I want to invert. Similarly, let's go over to cosine. So I'll start at x equals 0. How far to the right can I go before I stop being 1 to 1? How far to the right can I go before I violate the horizontal line test? Let's see. So far, so good. So far, so good. I reach this minimum, though, and at that minimum, I would turn around. And as soon as I turn around, one could draw a horizontal line that crosses the graph twice. And you want to forbid that. So you can't go beyond x equals pi. So that's the point pi comma negative 1. How far to the left can we go? Well, let's see. If I start here, this color, and I go to the left at all, well, I immediately violate the horizontal line test. So I just can't go left. So I'll only take that bit of the graph of sine and the graph of cosine, which happily are pre-graphed here electronically. So let's now just look at those pictures. So if I take the graph of y equals sine of x and I restrict its domain to negative pi over 2, and I take the graph of cosine and I restrict its domain to be 0 comma pi, well, I know this is going slightly out of order. I'm not going to fill in the range yet. Let's ask ourselves, if you just saw the graph of this and the graph of that, would you say that each of those is 1 to 1? Yeah, of course you would. They both pass the horizontal line test. So they have inverse functions. Let's go ahead and also determine the range. So by looking at the graph, you can determine the range. So what is the range of this one? Well, what y values do you see on the graph? Well, you see a minimum of -1, you see a max of 1, and you see all the values between. Similarly, what's the range of cosine when you restrict its domain? Again, you get -1 to 1. And that should be encouraging, because what's the range of cosine if I allow x values that are anywhere? Also -1 to 1. So I at least get all of the possible outputs even after I restrict the domain. There was no guarantee that I could, but it looks like I can. Cool. So these functions have inverse functions. Definition. Sine inverse, also called arcsine, is the inverse to sine of x after you restrict the domain with the domain of sine of x restricted to -pi/2, comma pi over 2. Now you might object and say, well, -pi/2 to pi/2, that's like an arbitrary choice. You could have picked the domain differently. And that's true, you can. And it is an arbitrary choice, but it's nice to make the choice that contains 0 and some positive numbers. Inverse cosine, also called arc cosine, is the inverse function to cosine after you restrict the domain of cosine to be 0, comma pi. So let's go ahead and read these off. So what is the domain of inverse sine? Well, the domain of inverse sine should be the same as the range of sine after you restrict the domain of sine. Well, what is the range of this? Well, we just found it. It's -1 to 1. So that means that the domain of inverse sine is -1 to 1. What is the range of inverse sine? Well, the range of inverse sine should be the same as the domain of sine after we restrict the domain. And what do we restrict the domain of sine to in order to get an inverse function? Well, that. Similarly, what is the domain of inverse cosine? Well, it's the same as the range of cosine, -1 to 1. What is the range of inverse cosine? Well, it's the same as the domain of cosine after we restrict the domain. Nice. And we'll do a few more things. I'll try to cut this video off reasonably soon. By the bottom of this page. Let's think about their graphs. So if you want to understand the graph of sine, well, I know how to graph a function. I know how to graph an inverse function if I know what the graph of the original function looks like. So here's the graph of y equals sine of x with its domain restricted to -pi/2 to pi/2. How do you get the graph of the inverse function? Well, you flip all of the x and y, x's and y's. You reflect over the line y equals x. So, doing that, well, I see this point here where it looks like it has, the graph of sine has like 0 slope. There's min there. So there should be instead infinite slope, and then it should level off. And instead of going towards the point pi/2, 1, it should go to the point 1, pi/2, right? X and y coordinates will get switched. All right, same thing for cosine. So cosine, the graph of cosine goes through the point 1, 0, 1. So the graph of inverse cosine will go through the point 1, 0. And the graph of cosine at 0, 1, you see it has like no slope. It flattens out at x equals 0. So here it should have infinite slope. So it should be really, really steep. I see this, oh, that's a problem, pi/2, 0. That'll be fixed in the online version. So that point, when I switch the role of x and y, will become the point 0, pi/2. over 2. So it'll be really steep. We'll get to there. It kind of flattens out to have slope about -1. Slope 1. No, -1. And then it climbs up to -1 comma pi. So there's the graph of inverse sine and inverse cosine. And because I want to demo some computer-y things, let's pull up a computer and just look at computer-generated graphs of the same. All right, and there we are. Here we have the graph of arc sine in red. And there we have the graph of inverse cosine, also called arc cosine. And that's about what we drew, qualitatively anyway, right? Nice. So let's just read some things off. It looks like inverse cosine is always positive. It's decreasing though. It has an x-intercept at 0 comma pi over 2. Inverse sine is increasing on its whole domain, passes through the point 0, 0. Nice. So, let's see, I think I will stop the video here. We'll come back next time and we'll think about just another philosophy for thinking about inverse sine and inverse cosine, which will seem a lot like the same philosophy again. We'll use it to make some computations, then we'll study just some of the behavior of these functions.